So yeah, my name is Jordan. I was not aware that that video was going to be there, so I actually have like a slide of intro about me, but you already know the most important stuff, I guess. Previously studied computer science, AI back in France, Stanford for a little bit, worked on self-driving cars for a while at Cruise. Then I started getting into hacking game consoles, which is what you're seeing there. This is a 3DS, this is a Wii U. Fun consoles, more fun if you hack them, and somehow that got me to work at Microsoft. I now work on the offensive security research team under David Weston, and basically what we do is we write exploits. Typically for Microsoft products, the idea being that if we write exploits, we can discover new exploit techniques, and if we discover new exploit techniques, we can start mitigating those before they're actually being used in the wild. So trying to be, the elite advanced hackers of the company, or at least some of them, and succeeding for the most part. So what my talk is about today is browser security beyond sandboxing, which is kind of a vague title. The real reason for that title is I didn't want to call it Let's Hack Chrome, which is what this really is going to be about. Just to give a quick rundown of what we're going to be talking about, first I'm going to just talk about the different security strategies of Chrome versus other browsers, and then going to do a deep dive into the bug that we actually exploited to get remote code execution in Chrome, then going to do a live demo of what that entails in practice, and then going to go over what we did, what can be done to be done better, and what is being done, and all that stuff. So just so you know, there will be a live demo at some point, so if you get bored, please don't leave. It's going to be fun-ish, going to do my best. So you might be wondering, why me as a Microsoft hacker would I go hack Chrome? Well, it turns out that Chrome has a slightly different security strategy from our own browser, which you might have heard of. It's called Edge. And I'm not the one saying that, right? So this is Justin from Google Chrome security team saying that, almost word for word, that Chrome is investing very heavily into isolation, whereas Microsoft has been making much heavier investments into RC mitigations. I would say that that's true to an extent. It's definitely true that we've been making some big investments into RC mitigations. You can see that with control flow guard, so CFG, CFG export suppression, which is more recent, ACG, which actually prevents the generation of any kind of dynamic code within the Edge content process. This is like the JIT compiler is all inside of a separate process, so you have some isolation there, but it's also like it's really an RC mitigation. And so we've definitely been making some investments there that have not been made by Google, but we have also been making some pretty strong isolation investments, I would say. So for example, in R3 we shipped less privileged app container, so LPAC, which drastically reduces the attack surface on the sandbox from within the Edge content process. And obviously we're also shipping Windows Defender Application Guard, which just isolates the Edge browser into its own virtual machine. So I would say that we are also making some pretty strong statements in the isolation field, but it's certainly a different strategy than what Google is doing. In terms of what that looks like in practice for Google, well, that would be their sandbox model, basically. Don't take my word for all of this. I'm just a Microsoft engineer. I don't actually work on Chrome. This is kind of an approximation of what I've been seeing, and I'm also the RC guy on the team. So don't just trust me on this, but it's mostly true, I would think. Basically, you can think of each renderer process as being its own tab. That's not entirely true, but we'll go into that later. And so if you open one tab, you're going to have one renderer process for it. If you open like a second tab that goes to like Bing, for example, you're going to have a second renderer process. And then the cool thing about these renderer processes is that they're going to be what is interpreting the HTML, the JavaScript for a given page, but it's not actually going to have any kind of privileges and access to any local resources in the machine. So for example, a render process actually can't really open any local files on your C drive, which is pretty cool because that means that if it gets compromised, an attacker has to take additional steps to do any kind of damage. If it actually does have a legitimate reason to open that file, it has to go through a browser process, which kind of brokers all of these interactions. Same thing, it can't call into things like Win32k, which is a pretty big attack surface. It has to go through a GPU process to kind of actually display anything on screen. So overall, it's a pretty strong sandbox model. On the flip side of this, though, we have a very soft RC target. As Justin was saying in that previous slide, we've been making, as Microsoft, making some pretty strong RC mitigation investments, but that's not necessarily been the case for Google, at least for Chrome. And an easy way to see that is this is just like latest version of Chrome as of yesterday, at least, Google Chrome version 63. If you just open VMMap and open a Chrome process in VMMap, you're just going to look for a little bit and find a bunch of execute read write pages. What that means in practice is that as an attacker, all we really need to do is find these pages and overwrite them, and all of a sudden you have code execution. You don't really need to do anything fancy. You don't need to do ROP. You don't need to do JOP or COOP or whatever people are calling it these days. You really just need to find these pages and overwrite them, and you have full code execution privileges. So I'm not saying that that's necessarily like a bad thing. That's kind of what we're going to be looking into, whether or not having RC within the renderer process is actually going to be strong enough for an attacker. But it's just a fact. Like, this is the current state of Chrome. So for this project, what we want to do is actually write real-world exploit to kind of get data on how soft of a target is Chrome in terms of RC, because I'm saying here it's a soft target in terms of RC mitigations. That doesn't really matter if you can't find a bug. So we need to find a real-world bug, see how hard it actually is to exploit, and then kind of work our way from there into what kind of damage a real attacker would be able to do with these kind of capabilities. So this is kind of my slide to plug, it's actually kind of cool to be a security engineer at Microsoft, because I didn't actually really do any work to find that bug. I just kind of stole a JavaScript fuzzer from the Chakra team, which is our in-house JavaScript engine. So they just wrote it for Chakra, actually, not even for security purposes, just kind of to make sure that Chakra even works. And then I used the security insurance team's fuzzing harness, just kind of plugged these things together, and I ran it on Azure, like on something ridiculous, like 1,000 machines. And thanks to that, within just a couple hours, I actually had an exploitable bug for Chrome. So I want to just plug, the whole, one Microsoft thing is actually kind of true, and it actually kind of works. It's actually kind of cool. Didn't really have to do any work and got a bug. So the only thing about that is this is fuzzing. So of course, the resulting, the result of this fuzzing process in terms of JavaScript is I'm going to end up with a gigantic JavaScript file of thousands of lines that don't make any sense. And you're going to try to figure out what the bug is from there. The truth is, I actually still don't really know why this bug happens. I didn't really try to root cause it, find the actual code inside of V8 that makes it crash. It just kind of does, and we are going to figure out how to exploit that just based on that without actually figuring out the root cause. Once you have these thousands of lines of JavaScript, the first step is basically to just kind of cut it down to as few lines as you can that still crash, and this is basically what that is. So you have a function, JavaScript function, func0, that is defined up there, and it doesn't really do anything weird, right? Well, I mean, it defines a local object, O, which has a bunch of properties, but none of the properties are doing anything fancy. It's just like, BAA is going to be 1.2, it's a float. Other things are going to be arrays or empty. Other things are going to be objects. And then it's going to call object.toString on one of these properties. And for some reason, this crashes on what looks like a null deref. You might not be able to see it very well there, but it's what it looks like. Something that is worth noting is that you don't actually just call func0 once. You have to call it in an infinite loop. And what that kind of indicates is that, well, there are two things that indicate that, but the first thing is, since just calling func0 once doesn't actually crash the JavaScript engine, that kind of indicates that it might be an optimization issue, right? Because as JavaScript JITs work, you just kind of call a function over and over again. At some point, the JIT is going to be like, oh, this is how this function normally runs. Let's try to optimize it for this specific scenario. And so the fact that it only crashes if you call it over and over again kind of indicates that it might be in that optimization pipeline. Another indicator of that is the fact that if you look at where the crash happens at the bottom left there, it actually does not happen in a fixed module. It happens as a JIT page. So that's another indicator that that might be the issue. Which is not super great because, optimizers are super complicated. I'm personally not a compiler engineer. I don't really necessarily understand how this stuff works, so that might be kind of annoying. But Fortunately, Google provides some really, really nice tooling for working with the JIT compiler, Turbofan, which was just shipped for V8 last year, V8 being the Chrome's JavaScript engine, just to be clear. And so you can actually use a tool called Turbolizer to represent the JIT's, to see how the JIT represents the code at different stages of the optimization pipeline. So this would be the high-level control flow version of the code that the JIT sees before optimization. And so what you can see here is you first have a call to toString, which is what we're seeing inside of func0 right here. That's a toString call right here. It's there. Then you have an infinite loop. That's what those yellow cells are. Those are just control flow indicators. And then you have another call to toString. So it's kind of weird that we have two calls, but this is just the JIT optimizer for some reason unrolling the loop. Sometimes it makes things better. In this case, it doesn't really matter. That's just how it is. But you don't really see anything interesting about the whole object stuff there, which is clearly important to the bug. So if we try to unwrap this with Turbolizer, we're going to get this. This is going to show us the entire generation, allocation, initialization of the object, and then how the object field is loaded and fed into toString. So if we look that into more detail, this is going to be the side that just kind of allocates the local object O, as well as some of its fields. Then you have object O.b, which is one of the fields of O, and then B.ba, and then that's just kind of all the initialization of the object on the local stack because it's a local variable. And then here you're going to have the piece of code that actually loads a field that is being fed as a parameter to the toString method. So at this point, this is before optimization, so everything looks fine. But if you go a little further into the optimization pipeline, this is after the escape analysis optimization phase. You're going to see you still have this object.toString call. You still have the object fields being loaded correctly. But if you look up there at the allocation of the object and the initialization of the object, for some reason, cell 264, which is supposed to initialize one of the fields of that object, is grayed out. So what that means is that that code is not going to be emitted. It's just, it used to be there, but it's grayed out, meaning that it got optimized out. So basically what it looks like is that Turbofan initially was interpreting the code correctly, but at some point, one of the optimization phases, in this case escape analysis, failed to realize that this field initialization step is actually necessary for this code to run correctly. And so what you're going to have here is that because store field BA right here is not actually running, load field BA is going to be loading uninitialized memory from the stack, from whatever memory is being used to load to store local variables. So we basically end up with the ability to manufacture code, JIT code, that just loads uninitialized memory and then interprets it as a pointer, which is super bad. So in terms of actually exploiting that, well, there are several phases. First thing is, as an attacker, we're living in a modern exploit world, so we actually have to do things such as bypass ASLR and such. So we kind of want to be able to first read data from memory before we actually want to corrupt anything. So the first thing you can see is in the initial version of the POC, you just have O.B.ba.bab, which is being loaded here, and that's what it's crashing on. And this is the instruction that is being crashed on. At this point, is actually loading it as a pointer and interpreting it as such. So what we can do is change BAB from being an object, in this case an array, to being a float and seeing what that changes. And that actually changes it from being interpreted as a pointer, an object pointer, into being interpreted as a double value, which is pretty cool because that means that whatever is going to be read, assuming that you can get this to be read from a valid pointer, which we're going to look into later, then you're actually just going to be getting a float back. You're not going to be getting an object pointer, and that's good because if we were getting an object pointer back, then we would probably be crashing unless we actually had a valid object at the other end of that. So this is a good first step to getting an info leak. The second thing is we can actually control which offset these values are going to be loaded from. So since this is all happening within this local object with a bunch of different fields, if you just add a number of fields with, the contents don't really matter, it's actually going to change the offsets that these values are going to be loaded from. In this case, we're getting 0 being loaded from rbx plus some offset, and we can actually control what some offset is just by adding more and more fields. So we're getting more and more control over what's happening there. The only thing is, we're still, loading some random value from the local variable space, which is not great. And so ideally, we want to be able to place our own custom pointer there or whatever else. And so it turns out if you just create an array which has a bunch of different values in it, it's actually all going to be allocated into that same space. So you can just spray different values. It's basically a heap spray. Hey there. It's actually kind of heap spray, but it's more of a stack spray, really. And so you're going to have the ability to place arbitrary values there. And so these are all going to be loaded there. And then since you can control the offset that your pointer is being loaded from, you can just make it fall into one of these red areas instead of falling into one of the rando other areas. And so the result of this is we actually have 3 primitives from this one bug. The first primitive is if we spray a JavaScript object pointer, we know it's going to be a valid pointer, and we can just read the result as a double value, then we're going to have an info because we suddenly have the ability to read any arbitrary member variable from that object. So from there, you can leak a valid pointer. You can leak, for example, if you were to spray a JavaScript object that's, say, an array buffer, you could leak the location of the actual buffer. So that gives you an ASLR bypass, which is super, super nice. Then the next thing is if you were to spray a double value, you could spray any arbitrary pointer there and then read back as a double value. Then all of a sudden, you have the ability to read arbitrary memory from JavaScript. And this is all with just this one bug, nothing more, nothing fancy. So that's, again, a super powerful primitive from this one bug just by changing things up a little bit. Then the third primitive you're going to have is the nicest one. If you spray an arbitrary double value, which is going to be a valid pointer, which you're able to manufacture because you already have these info leaks above there, and you load the result as being a JavaScript object, so like a JavaScript object like it was before here, like BAB is a JavaScript object, so it's going to be interpreted as a JavaScript object. In that case, you actually have the ability to create arbitrary JavaScript objects, which might not sound super exciting, but it really is. What that means is, personally, what I like to do is to create an arbitrary data view object. I'm just going to create a fake array buffer, fake data view object, and then I can modify the address of the buffer of that array buffer, and then all of a sudden I have the ability to read and write at arbitrary locations from JavaScript. So this is just example code that lets you read from an arbitrary location from JavaScript using this fake data view object. The syntax is kind of weird because I'm actually not initializing all the fields inside of that fake data view object because that's kind of annoying, but this all works, and that gives me the ability to kind of read and write whatever I want, which, if you'll recall, is all I need to get code execution because we have read, write, executable pages. So basically, it's just 2 steps to getting code execution. It's just to first find one of these RWX pages, which is trivial. All you have to do is find a JavaScript function object, read the entry point from it, and then write to it, and then you just call that JavaScript function, and you have code execution. So we have remote code execution, which is great. Just a side note of how to make things a little cleaner. Beyond just having random shell code here, we are actually going to be downloading a reflective DLL over an XHR request, just loading that in memory somewhere, and then what the initial shell code that is being copied over a JIT page is going to do is going to call virtual protect over that reflective DLL, call into reflective DLL, and then you have a nice kind of environment that you can just compile in Visual C++, and it's much nicer than doing everything in assembly. And so at this point, where we are, this was the sandbox model. I have access to one of the renderer processes, and, well, that's it. At this point, I'm kind of stuck. It's like, yeah, I can execute code. This is pretty great. Keeping in mind that this was all written before all of the Spectre Meltdown stuff. So at this point, actually, with Meltdown before mitigations, I'll also be able to read kernel memory, which would be pretty cool. But let's kind of ignore that. and think of, oh, well, what can I do from there? I have access to one render process, for example, from my personal attacker website, but I can't even access data from other websites because those are in other processes. And I can't access local files, I can't access the GPU, I can't really do anything. So that's when the demo comes in. Because you actually can do stuff, just to be clear. All right, so this is a VM right here. And hopefully this works. I tried a bunch of times today, and it worked every time. So if this does not work, I'm going to be pretty sad. OK, so let's assume you're a user. You're using Gmail because you need to. And you get this email, right, from someone who says, oh, you should definitely click that link. And, I mean, it's probably a friend, so you're going to click that link. And you kind of, God damn it, you kind of click that link, and this didn't just happen. I swear to God. This was definitely working 5 minutes ago. OK, well, it's actually not, yeah, the server crashed, just a sec. OK, yeah. Wait, can it? Ooh. OK, so I think it worked. So had this worked, flawlessly, as it usually does, you would have just seen, oh, OK, you click that link, and something happens real quickly, and then you're on Google here. You can actually close that, and nothing weird seems to have happened, beyond the whole crash there, which you did not see. So right now, I'm just going to minimize this and open Chrome on the host, because this was something else. And I'm going to log into my beef interface. And oh, what do you see? There's actually a bunch of beef interfaces here. Even though, if you'll recall, there was no, there's no Gmail thing open anymore. There's just Google, nothing else. And yeah, I have a beef interface connected to Gmail here. And I can use this to hopefully steal some Gmail email. Come on. Yay. So these are all the emails that were in the inbox, which is kind of cool. And then I can do other things, such as navigate somewhere else. So let's go to github.com, log in, because that's what we want to do. I'm just going to navigate there again. Navigation should have happened, and hopefully something shows up. Actually, I should just be able to steal some passwords. Come on. OK, it's supposed to work. Again, live demos are a bad idea. Come on. All right. So beyond some, I'm an exploit developer in-house. I don't make production-grade stuff. But if you'll take a look here, and I'm going to zoom in if possible. OK, it's not. Oh. All right, it's not working. Yeah, so if you take a look here, anyways, you have the actual email account for that GitHub account, and you also have the password. So if someone here has a phone or a laptop, you can actually try to log into my fake GitHub account right now, because this was actually able to steal these passwords, which should be kind of cool. Thank you. And so just to give an idea of what the magic that's going on here, again, you just kind of have this Google window. It's not, nothing is really crazy here. And yet, if you take a look at the Chrome Task Manager, you have this Google tab right here, but you also have a GitHub tab, even though you're not seeing anything. And if you double click it, oh, there's a little window here. Oh, there's a little window here. And yeah, so it turns out when you actually run the exploit, it kind of does a pop under right there, and you don't really see it because having code execution, you can actually bypass a bunch of user interaction checks, and you can do a bunch of stuff that you're not supposed to be able to do, such as, for example, and this had better work, I'm going to close this window, and hopefully, it didn't work. OK, I'm going to close this window. And yeah, okay, so the idea was whenever you close a window, one of these pop-unders, it's actually supposed to like pop back up. The network issues here are probably not making this any better, but that's the theory. So what you saw there is I closed the window. It just created another pop-under as the window is being closed. But yeah, there's network issues, so it's not actually working. But oh, it is working now. So yeah, if I close this, there should be another one. Yeah. Basically, the idea is like for a regular user, you're just going to be closing these, and they're just going to keep popping up, which is super annoying. Like this is not going to be targeting probably like anyone in this room, but if you're targeting like a grandma or something, you're going to be able to just like persist as long as she doesn't reboot your computer, her computer, which is a pretty good primitive, I would say. Oop, wrong slide. Yep. And so that was the idea. So at this point, how we actually make all that magic happen. So the first thing that you want to realize is, even though I said that one renderer is typically one tab per process, it's actually not. So this is what I was just showing you, is you can actually get multiple tabs to spawn inside of the same renderer. That's kind of an isolation failure, but that's what every browser these days does because resources are not free. You can't just be creating processes anytime you navigate to something. Typically, it will create a new process, but as an attacker, you can be kind of smart and force it to not create one. So that's the first trick, which makes it so that getting code execution inside of a Google tab gives you access to all the content in the Bing tab, for example. Which is useful as an attacker because I don't want to be stealing data from my own website. The other trick being the immortal pop-unders. As I mentioned, having code execution means that you can bypass a bunch of checks that are happening inside of a renderer, which means that those checks should probably not be happening inside of a renderer. Ideally, interaction checks should be happening in something higher level, like the browser process, which the attacker would not have access to at this point. And so that way you would not actually be able to create these pop-unders, and you would hopefully not be able to just keep those pop-unders popping back up. But at the end of the day, this is just very simple. I'm just literally patching in 3 bytes of code, and then I have the ability to create arbitrary numbers of pop-unders from JavaScript, and it makes things real nice. When I say that ideally this is what should be happening, I believe that Edge is doing the same thing at Chrome, so I'm not trying to say that Chrome is bad or anything. It's just like this is how things currently work, and this is how these things can currently be exploited. The other thing that I'm doing is I'm actually injecting code that makes it so that my JavaScript has access to more than it should have. So for example, I'm going to be able to write arbitrary memory. I'm going to be able to steal passwords all from JavaScript just thanks to this custom interface I'm creating. Custom interface being nothing fancy, I'm really just overriding a JavaScript function that is accessible normally and making it so that under certain circumstances, with like a magic number and everything, is going to interpret the data inside the array as a kind of command. So again, nothing fancy. This is just kind of an easy way to do it. Same thing for getting universal cross-site scripting, which is going to be a way for me to kind of inject arbitrary JavaScript inside of any new frame that is actually spawned inside of my process. I am just going to hook this classic script run script function inside of the Chrome DLL binary, and not really doing anything crazy. Really, just creating a new WTF string, embedding that string into the current script that's about to be executed, and then letting the things execute as expected. So now another interesting thing is going to be the aftermath of this, which I have to give props to Google. They were really reactive in terms of actually fixing this bug. I think the first commit that fixed this bug was committed 3 days after we reported it, so very impressive agility. And then same thing, the actual fix was shipped 4 days after that. So that's a 1 week turnover, very impressive. Maybe a bit too impressive, actually, in some respect, is what I want to show right after. Kind of something that I want to point out is something that we noticed is that the code of V8 being publicly available on GitHub is great until you start publicly fixing security bugs before actually servicing it to users. So that's what this is showing here. This is actually a commit for a security bug that was made back in May 2017. And it had everything, all the details of what the bug was, how it was fixed, as well as a regression test. So you actually basically have an exploit POC right there on the GitHub. And that wouldn't be an issue. Open source is great, unless you were to publish that fix on GitHub a whole month before actually shipping the fix to the stable channel of Chrome. So it's kind of problematic because there being no RC mitigations in Chrome basically means that you have a POC, within a day you're going to be able to get code execution, and all of a sudden you're being able to steal data like I was just demoing without really much work to be done. So not great. Beyond that, I do want to point out that Google has been working on site isolation for a while. They are shipping this as I'm speaking right now. Basically what site isolation means is that this kind of attack would not be possible anymore. You would actually have a single process per tab, per origin, really. And so even actual iframes would be isolated in separate processes, which obviously is where everyone wants to be in the browser space. The problem is, as it says here, you have a 10 to 20% overhead in certain scenarios, which is not necessarily acceptable for everyone, especially in mobile browsing, which is the bulk of the market these days. So this is something that they are working on and doing a great job, but we're not quite there yet. And so as a conclusion, I want to say that browser RC is still a significant threat, which is kind of being underestimated, I believe. And just want to reiterate that just focusing on isolation is super great, but it's not the only thing that needs to be done. I do believe that focusing also on RC mitigations is important, especially because RC mitigations end up hardening your isolation surface as well. If your broker process has no RC mitigations, then you're making that surface much weaker as a result. And so you should kind of just do that across the board. And yeah, thanks for your time. If you have any questions, we don't have time for that.